So for this question right here, we've got a long thin rod. It has a non-uniform charge density, and we want to find an expression for the potential at point P. Like I talked about in class, this is a pretty complicated problem, and this is harder than something I would give you on this year's final exam. In the meantime, if you're interested, I'll set it up for you. If you're not interested, don't worry, you don't have to go through it and figure out. But if you'd kind of like to see where the answer comes from, I'll take you through it. So the deal is, because we have a non-uniform charge distribution, we can't really just integrate over the rod from 0 to L. So it's non-uniform, there's different bits of charge everywhere. And when you have your dq on this side, it's different from when you have your dq on this side. Okay, so let's just kind of break it down. Let's find the potential from the left half of the rod. So let's start there. We've got a dq. It's at position x, and it has a thickness of dx. From dq to our point P is a distance of r. So our potential for the left half, and I'm not going to go through all of this, I'll start it and then I'll give you the answer. For the left half, our total potential on the left is equal to the sum of each little bit of potential made by each little bit of charge dq. Each little bit of potential is given by k times dq divided by r. dq is equal to the charge density times the thickness. The charge density is some constant times the position. Okay, so there's our dq. R is the hypotenuse of a right angle triangle where the two legs are from here to here and from here to here. The length of this leg is this length take away x. So R is going to be the square root of L over 2, that's this much, subtract this much, square it, add it to y squared, take the square root, there's our R value. Okay, now we've got something for dq, we've got something for r. The potential due to the left half of the rod is k times a times x times dx divided by r, which is the square root of L over 2 minus x squared plus y squared. This one is hard to integrate, so we need to do a substitution. Let's let x primed equal to L over 2 subtract x. This means that dx primed is negative dx. Putting that in this expression, we get an integral k times a times L over 2 subtract x primed. So x primed is L over 2 minus x. It means x is L over 2 minus x primed times dx primed negative divided by the square root of x primed squared plus y squared. Okay, this is an integral you can deal with. The last thing we need here are our limits. For this integral, where it's in terms of x, we go from x initial to x final. X initial is one end of the rod, equals 0. X final is where we stop halfway through, L over 2. This integral is in terms of x primed. So x primed initial is going to be L over 2 subtract x initial equals L over 2. X final primed is L over 2 subtract x final equals 0. So the limits of this integral are from L over 2 to 0. Dot, 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 follow through the process. I think you can take it from there. What you should get for your result is minus k times a times L divided by 2 times the natural log of y divided by L over 2 plus square root of L squared over 4 plus y squared plus k times a times y subtract k times a times the square root of L squared over 4 plus y squared. Alright, that's for the left half. We also have to do the right half, and then the total potential is what happens when we add them together. So now we'll look at this side of the rod. We'll pick this as our DQ. R is from here to here. And then on this side of the rod, our x coordinate